A reactor in a substation serves a crucial purpose. It limits the fault current to a safe level. Fault current, also known as short-circuit current, is the excessive electrical current that flows through a circuit during a fault condition such as a short circuit. This high current can cause significant damage to electrical equipment, including transformers, circuit breakers, cables, and other components within the substation and the broader electrical grid. The primary function of a reactor is to introduce impedance into the circuit, thereby reducing the magnitude of the fault current. Impedance is the total opposition to the flow of alternating current and consists of both resistance and reactance. By increasing the impedance, the reactor effectively limits the amount of current that can flow during a fault, protecting the equipment from thermal and mechanical stresses. The need for fault current limitation arises from the inherent characteristics of power systems. Power systems are designed to operate at a specific voltage and current level. During normal operation, the current flow is relatively stable and within the design limits of the equipment. However, when a fault occurs, the impedance of the circuit drastically decreases, leading to a surge in current. Without any means of limiting this current, the equipment would be subjected to extreme stress, potentially leading to catastrophic failure. The reactor achieves fault current limitation through its inductive reactance. Inductive reactance is the opposition to the change of current flow in an alternating current circuit due to the presence of an inductor, in this case the reactor. The inductive reactance is directly proportional to the frequency of the alternating current and the inductance of the reactor. The higher the inductance, the greater the reactance, and the more effectively the reactor limits the fault current. The reactor is strategically placed in the substation, typically in series with the circuit to be protected. This placement ensures that all fault current must pass through the reactor, thus experiencing the impedance it provides. The reactor is designed to withstand the high fault currents for short duration, providing sufficient time for circuit breakers to operate and isolate the faulted section of the system. The selection of a reactor for a specific substation application involves careful consideration of several factors. Firstly, the required impedance must be calculated based on the maximum fault current that the system can produce and the desired level of current limitation. This calculation takes into account the source impedance of the power system, the impedance of the transmission lines and transformers, and the ratings of the equipment being protected. Secondly, the reactor must be designed to withstand the thermal and mechanical stresses associated with high fault current. This requires careful selection of materials, insulation, and mechanical support structures. Thirdly, the reactor must be designed to minimize losses during normal operation. While the primary function is fault current limitation, it is also important to ensure that the reactor does not introduce excessive voltage drops or energy losses under normal operating conditions. There are different types of reactors used in substations, each with its own advantages and disadvantages. Firstly, air core reactors are widely used due to their simple construction, high reliability, and low cost. These reactors consist of a coil of conductor wound on a non-magnetic core, typically air. The absence of a magnetic core eliminates the risk of saturation, which can occur in iron core reactors under high fault current conditions. Air core reactors are also less susceptible to harmonic distortion and can withstand higher transient voltages. However, air core reactors tend to be larger and heavier than iron core reactors for the same impedance rating. Secondly, iron core reactors use a magnetic core to enhance the inductance and reduce the size of the reactor. The magnetic core is typically made of laminated steel to minimize eddy current losses. Iron core reactors are more compact and lighter than air core reactors, but they are susceptible to saturation and harmonic distortion. They also require careful design to mitigate the effects of core losses and stray magnetic fields. Thirdly, oil-immersed reactors are used in high-voltage substations where insulation is a critical concern. These reactors are immersed in oil, which provides both insulation and cooling. The oil helps to dissipate the heat generated by the reactor and prevents flashover between the windings. Oil-immersed reactors are typically used for high-impedance applications where air core reactors would be excessively large. The benefits of using reactors in substations extend beyond equipment protection. By limiting fault current, reactors also enhance the stability of the electrical system. During a fault, the voltage in the affected area of the system can drop significantly. This voltage drop can cause other generators in the system to become unstable, potentially leading to a cascading outage. By limiting the fault current, reactors help to maintain the voltage level during the fault, preventing the loss of synchronism and preserving system stability. Reactors also play a role in improving the power quality of the electrical system. Fault currents can cause voltage sags and swells, which can disrupt the operation of sensitive electronic equipment. By limiting fault current, reactors help to reduce the magnitude of these voltage disturbances, improving the overall power quality and reliability of the system. The operation of a reactor is relatively simple. Under normal operating conditions, the reactor presents a low impedance to the flow of current. This means that the voltage drop across the reactor is minimal and the energy losses are low. However, when a fault occurs, the current increases rapidly. The reactor's impedance increases proportionally with the current, limiting the fault current to a safe level. The reactor is typically protected by circuit breakers, which are designed to interrupt the fault current if it exceeds a predetermined threshold. The circuit breakers operate quickly, isolating the faulted section of the system and preventing further damage. The coordination between the reactor and the circuit breakers is crucial for ensuring effective fault current protection. The maintenance of reactors is relatively simple. Regular inspections are required to check for any signs of damage or deterioration. The connections must be checked for tightness and corrosion. The insulation must be tested to ensure that it is in good condition. Oil-immersed reactors require periodic oil sampling and analysis to check for contamination and degradation. The installation of a reactor involves careful planning and execution. The reactor must be properly sized and rated for the specific application. The installation location must be chosen to minimize the impact on the substation layout and the surrounding environment. The connections must be made securely and according to the manufacturer's recommendations. The testing and commissioning of a reactor are essential to ensure that it is operating correctly. The impedance must be measured to verify that it is within the specified tolerance. The insulation must be tested to ensure that it is capable of withstanding the operating voltage. The cooling system, if applicable, must be tested to ensure that it is functioning properly. In summary, the purpose of a reactor in a substation is to limit fault current to a safe level, preventing damage to equipment and ensuring the stability of the electrical system. Reactors achieve this by introducing impedance into the circuit, thereby reducing the magnitude of the fault current. Reactors also enhance the stability of the electrical system by helping to maintain the voltage level during a fault, preventing the loss of synchronism and preserving system stability. Reactors also play a role in improving the power quality of the electrical system. There are various types of reactors such as air core, ion core, and oil-immersed reactors, each having their own characteristics. The selection, operation, maintenance, installation, testing and commissioning of reactors are essential to ensuring a reliable power distribution system. Reactors are an integral component of modern substations, providing essential protection against fault currents and contributing to the overall reliability and stability of the electrical grid. Without reactors, substations would be vulnerable to catastrophic damage, leading to widespread power outages and significant economic losses. When evaluating the impact of a reactor, it's important to consider specific scenarios. Firstly, consider a scenario where a fault occurs close to a large power transformer. The potential fault current could be extremely high, exceeding the interrupting capability of the circuit breakers and potentially damaging the transformer itself. A reactor placed in series with the transformer would limit the fault current, allowing the circuit breakers to operate safely and protecting the transformer from damage. Secondly, imagine a situation where a fault occurs on a transmission line connected to the substation. The fault current could cause a significant voltage drop in the area, potentially affecting the operation of other equipment connected to the same bus. A reactor placed in the substation would limit the fault current, mitigating the voltage drop and preventing disruption to other equipment. Thirdly, in a scenario involving a distributed generation source, such as the solar farm or wind farm, connected to the substation, a fault on the distribution system could result in a high fault current contribution from the distributed generation source. A reactor could be used to limit this fault current contribution, preventing it from exceeding the substation's equipment ratings. The application of reactors is also governed by various standards and regulations. The Institute of Electrical and Electronics Engineers, known as IEE, provides standards for the design, testing, and application of reactors. These standards specify the performance requirements for reactors, including their impedance, current carrying capacity, and insulation levels. The National Electrical Code, known as NEC, also provides guidelines for the installation and protection of reactors. For example, NEC Section 470.1 provides requirements for the location and guarding of reactors. The development of reactor technology is ongoing. Researchers are constantly working to improve the performance, efficiency, and reliability of reactors. One area of focus is the development of new materials with higher magnetic permeability and lower losses. Another area of focus is the development of advanced cooling techniques to improve the heat dissipation of reactors. Furthermore, the integration of smart grid technologies is also influencing reactor design. Smart grid technologies allow for real-time monitoring and control of reactors, enabling them to be dynamically adjusted to optimize system performance and stability. Reactors not only protect equipment and improve system stability, they are also important for maintaining power quality. Voltage sags and swells caused by fault currents can disrupt the operation of sensitive electronic equipment. By limiting fault current, reactors help to reduce the magnitude of these voltage disturbances, improving the overall power quality and reliability of the system. This is particularly important for industrial facilities and commercial buildings that rely on sensitive electronic equipment for their operations. In the context of renewable energy integration, reactors play a critical role. As more renewable energy sources, such as solar and wind, are connected to the grid, the potential for fault currents increases. Renewable energy sources often have different characteristics than traditional generation sources, which can lead to higher fault current contributions during fault conditions. Reactors can be used to limit the fault current contribution from renewable energy sources, preventing them from exceeding the substation's equipment ratings and ensuring the stability of the grid. The environmental impact of reactors is also a consideration. Reactors can generate noise and electromagnetic fields. Noise can be mitigated by using sound barriers and vibration damping materials. Electromagnetic fields can be minimized by using shielding and proper grounding techniques. Oil-immersed reactors also pose a risk of oil spills, which can contaminate soil and water. Therefore, it is important to implement proper spill prevention and containment measures. In summary, the reactor plays a multifaceted role in substations. Its ability to limit fault currents not only protects valuable equipment, but also contributes significantly to the stability, power quality, and overall reliability of the electrical grid. As power systems evolve with increased integration of renewable energy and smart grid technologies, the importance of reactors will continue to grow. Continuous advancements in reactor technology and adherence to established standards and regulations will be crucial in ensuring their effective and safe operation.